Have you ever wondered what the burger you ate for lunch has in common with the gas in your car? Or maybe an instant cold pack you'd use for a sprained ankle? It seems like they have nothing in common, right? Well, it turns out they're all connected by this incredible invisible science that's all about heat and energy. So let's dive in and uncover this hidden world of thermochemistry. All right, let's start with something we all know and love, a cheeseburger. We look at this and we think, fuel, right? Energy to get us through the day. And you're not wrong. But how your body actually unlocks that energy, well, that's where the real science kicks in.
But this is the big question. How on earth does that burger connect to something that gets intensely cold, like an instant cold pack, or to something that creates a controlled explosion, like gasoline? One gives you energy, one gets cold, one gets hot. What's the secret link?
Turns out the answer is a single fundamental science. It's kind of like a rule book for energy that explains how it moves and changes in every one of these situations. It's the invisible force connecting them all.
And that science is called thermochemistry. It's the branch of chemistry that's all about the heat and energy changes that happen during chemical reactions. This is the key that unlocks the whole mystery. It shows us that a burger, a cold pack, and gasoline are all just playing by the exact same rules.
So to really get this, we need to boil it down to the most basic idea in thermochemistry, the two main types of reactions. And honestly, it's pretty simple. It's all about things that get hot and things that get cold.
Okay, so on one hand, you've got something like this oxyacetylene torch. This reaction releases a ton of energy as heat and light, enough to slice right through solid steel. And then, on the other hand, you have a cold pack. You break that little pouch inside, give it a shake, and bam, it gets incredibly cold. It's actually sucking heat right out of the air. And you.
So, here's the most important takeaway. It's all about the direction the heat is flowing. Is heat shooting out into the world, or is it being pulled in from its surroundings? Honestly, that's the whole game right there.
Now, this is a great way to visualize it. Scientists call the chemical reaction itself the system. So in one case, you can see heat is exiting the system and flowing out into the surroundings. In the other, heat is entering the system, pulling energy from the surroundings. This leads us to two super important terms.
First up, we have an exothermic process. This is any reaction that releases heat. The burning torch, the gasoline in your car, and yeah, even your body digesting that burger, they're all exothermic. And here's an easy way to remember it. Exo sounds like exit. The heat is exiting the system. Simple as that. And the opposite of that is an endothermic process. This is any reaction that absorbs heat from whatever is around it, making those surroundings feel cold. That instant cold pack? Classic endothermic reaction. And the little memory trick works here too. Endo kind of sounds like enter. Heat is entering the system.
And this chart just lays it all out perfectly. For exothermic reactions, energy is a product. It's spit out, making everything hotter. But for endothermic reactions, energy is a reactant. It's something the reaction needs, so it gets gobbled up from the surroundings, making things colder. Think about it. A campfire releasing heat versus a plant absorbing sunlight for photosynthesis. Same exact principle, just going in opposite directions.
Okay, so now that we've got that down, let's circle all the way back to that burger. How do these ideas about hot and cold reactions apply to something we literally count every day, the calories in our food? So the stuff in our food, the fats, the proteins, the carbs, that's our body's fuel. Our metabolism is just a series of super complex, very controlled exothermic reactions. Our bodies break down this fuel to release the energy that's been stored up in its chemical bonds.
So, when you say you're getting energy from your food, you're not speaking metaphorically. Not at all. You are literally talking about thermochemistry. You are kicking off a chain of heat-releasing exothermic reactions right inside your own cells.
And this is why what you eat matters so much from an energy perspective. You can see on this chart, fats pack more than double the energy potential per gram, we're talking 9 calories, compared to carbs or proteins, which both give you about 4. And that isn't just some random number. It's a direct measurement of how much heat gets released when your body breaks that substance down.
Now check this out. This is a really cool fact. The calorie you see on a nutrition label, the one with a capital C, is actually a kilocalorie, and that's a scientific unit of heat. It's the amount of energy needed to raise 1 kilogram of water by 1 degree Celsius. So a food's calorie count is literally a measurement of its thermal energy. You're eating potential heat.
Okay, so we've seen thermochemistry working inside us. But these exact same principles, releasing heat and absorbing heat, they apply everywhere. From little products you can hold in your hand to massive weather systems that stretch for hundreds of miles.
So let's look at two super common examples. The instant cold pack is endothermic. You mix water and a special salt, and that reaction needs energy. So it pulls that energy in as heat from its surroundings, like your sore ankle. On the flip side, those reusable hand warmers are exothermic. When you click that little metal disc, it starts a rapid crystallization process, and that chemical change releases a whole bunch of heat.
What is just mind-blowing is that these basic ideas don't just work in tiny packets. They scale up, way up, to drive enormous systems that actually shape the world we live in.
Take a huge weather event like the Santa Ana winds. Basically, as air gets forced up over a mountain range, it cools down and drops its moisture. But then, as that now dry air rushes down the other side, it gets compressed like crazy. That compression is an exothermic process. It releases a massive amount of heat, creating those famously hot, dry winds. It's the same idea as a hand warmer, just on a planetary scale.
So you might be wondering, how do scientists figure all this out? How do they predict how much energy will be released or absorbed? Well, one of their best tools is something called Hess's law. It's a simple but totally brilliant idea. It says the total energy change is the same no matter how many steps it takes to get there. It lets scientists solve for the energy of a really complex reaction by adding and subtracting simpler building block reactions, kind of like solving a puzzle.
And this is why it's so important. Hess's law gives science predictive power. It lets engineers calculate the energy they can get from a new rocket fuel before they even build the engine. It helps chemists design more energy-efficient factories to make all the stuff we use every day. It is absolutely crucial for innovation.
So, there you have it. The same invisible science connects the energy in your food, the cold from an ice pack, and even the weather patterns outside your window. Thermochemistry is basically the rule book for how energy flows all around us. So now that we understand the rules of the game, the really big question is, how can we use them better to build a more efficient and sustainable future?